Have you ever wondered what would happen if the movie Armageddon happened on steroids? Yeah, us too. This is what prompted us to ask, what if an asteroid descended upon the Earth at half the speed of light? To begin, we have to determine what our asteroid looks like. To do this, we decided to find the most average asteroid out there. We assigned arbitrary values for the asteroid's mass. Also, because the Earth is an oblate spheroid, it does not have a uniform diameter, so we averaged the diameter, which came out to 12,800 kilometers, and we know the Earth has a mass of 5.9 times 10 to the 24th kilograms.
A key factor in showing just how screwed we are is showing how much kinetic energy is released. Though, because it's going faster than a JK 2006 portable bag closer at maximum speed, the universe has other plans. We'll have to use the relativistic kinetic energy formula. Since we already know light speed, and the speed of which the object is moving, plugging in those values into the formula gives us a Lorentz factor of 1.15. We also already know mass, and again the speed of light, plugged into the formula gives us a kinetic energy of 4.05 times 10 to the 27th. So before the asteroid goes into the atmosphere, the kinetic energy is 4.18 times 10 to the 27th. Though this is with calculus in addition to physics, and since this is an algebraic class, we'll just treat this as a given.
We have found the kinetic energy of the meteor in a vacuum, but what happens to it when it enters Earth's atmosphere? In the Earth's atmosphere, we must consider how air resistance, material deformation of the meteor, and thermodynamic heating might affect the meteor. We can assume that this collision is perfectly inelastic, or about as close to perfectly inelastic as is possible in the real world, as almost all the kinetic energy will be transformed into thermal energy, radiated out, or transferred to debris that fly away from the impact site. With this assumption, we can calculate how much air resistance affects the meteor using this formula.
We can do this by finding the mass of the column of air the asteroid comes into contact with and plugging it into the same relative kinetic energy formula. The area of the air the asteroid comes into contact with is solved for here. We also identify that we're going to be using atmospheric pressure, and F equals ma, where a is equal to g, which is 9.8. We now have our area and we have the equation we're going to be using, and so here we solve for mass by plugging in our variables. And so mass was 2.03 times 10 to the 11th kilograms. We can then use this mass to solve for the energy of the air. I'd like to note that we're treating the air as if the entire mass is hit at the same point, as if the asteroid just crashes right into the entire mass. This isn't too far off, as this happens over a very, very short time frame of like a really small fraction of a second. However, it's not entirely accurate and it is an approximation. You could calculate this completely without the approximation through the use of calculus, but this is an algebraic course, and so we didn't. Let's solve for time. Our velocity equals half the speed of light. The d equals the distance from the Earth's surface to the edge of its atmosphere, which is the Kármán line. It's exactly 100 kilometers away. And so here we plugged into t equals d over v, and we got the time equals 6.67 times 10 to the negative 4th seconds for an observer standing on Earth. We can use the law of conservation of momentum in combination with relativity to find the velocity of the air molecules after the meteor collides with them. Note that the initial momentum of the air is 0, so our equation here reads, with relativity, gamma p asteroid initial equals the quantity p asteroid final plus p air final times gamma final. Note that gamma and gamma final are two distinct numbers. It's going to be important in a second. Substitute gamma final to accurately calculate v final using our given equation here. By multiplying all these values and solving for v final gamma final, we get this. We can also state that gamma final is equal to the Lorentz factor with v final as the velocity. We then can substitute this back in for gamma final. This is what we get. We continue our algebra here. Eventually we solve for v final, which is equal to 9.73 times 10 to the 7th meters per second, or 0.324 c. We can use the value of v final to solve for the final kinetic energy. V final equals 9.73 times 10 to the 7th meters per second, equals 0.324 c. Using this value, we can calculate gamma final. Gamma final, by plugging this in, equals 1.057. We plug this back into the same kinetic energy formula as earlier, and we get a kinetic energy final equal to 2.58039 times 10 to the 27th joules. The collision between the Earth and the asteroid will be almost completely inelastic, as the meteor becomes embedded in the Earth in the instant of the impact. We're going to treat it as completely inelastic. This means that we have to account for the conversion of the asteroid's new kinetic energy into thermal energy when the asteroid collides with Earth. This is an adiabatic process, as in the instant the asteroid strikes and the energy converts, no heat enters or exits the system. First, let's solve for temperature. As stated previously, all of the meteor's remaining kinetic energy is converted into thermal energy when it impacts on the Earth. We can use the Stefan-Boltzmann energy density equation to solve for the temperature of the meteor as it strikes Earth. U, energy density, which is energy over the volume, or here it's E thermal over V asteroid, and where A equals this, where that's the Stefan-Boltzmann constant. So this formula is normally used to calculate the density of energy in a black body. Due to the adiabatic compression the asteroid undergoes, it behaves like a black body. No energy goes in or out in the instant in which the asteroid impacts, and it is functionally opaque. Due to this change in energy, which facilitates a massive change in temperature calculated later, the meteor's matter changes phase to a superhot plasma. Due to the amount of energy the electrons have, they are completely free of their bonds in this instant, as the thermal energy is magnitudes greater than their binding energy, usually in the realm of 10 to the negative 17th joules. And the volume of the system decreases significantly, as the asteroid impacts and then gets crushed inward by its kinetic energy. This causes the free electrons to become so tightly packed that light cannot escape, making this system equivalent to a black body in this instant. We have U equals h to the 4th, and we've plugged in our numbers, and here we've solved for T equals 8.5 times 10 to the 7th Kelvin. Here's a diagram of an adiabatic compression, where the volume decreases and the pressure increases, but no heat leaves the system. So here we have our temperature again, which is 85 million Kelvin when the asteroid impacts. Initially, a radiation wave is emitted, so using Wien's displacement law given here, Where b is Wien's constant, we can find the wavelength of the wave, which comes out to be 3.413 times 10 to the negative 11th meters. This falls between the range for X-rays and gamma rays. We can solve for the wave's energy using the Planck-Einstein relation E equals HF. We found the energy to be 5.828 times 10 to the negative 15 joules. Visible light's energy lies in the realm of 10 to the negative 19th joules, while the radiated wave is in the realm of 10 to the negative 15th. That means that the radiated wave is around 10,000 times as energetic as visible light. We don't expressly need to know this information, but it's very important having a deeper understanding of how this collision would function and how the heating works. There's a critical temperature, 2.7 times 10 to the 6th Kelvin, that after becoming hotter than that, a system's energy is transformed almost completely into radiation, which is defined by the book Physics of Shockwaves, a text by these two authors. The extreme temperature of 8.5 times 10 to the 7th is more than 31 times this critical temperature, which allows us to state that in the equation we set up, E final equals E thermal plus K debris plus K seismic plus E radiation, can really just be simplified to E final equals E radiation, as all the kinetic energy becomes negligible. What does this mean? We can make an approximation of this value using Q equals mc delta T, where Q equals E final equals m atmosphere C air delta T. The mass of the atmosphere is 5.15 times 10 to the 18th kilograms, and the specific heat of air is given here as 1,000. We solve for delta T to equal 500,970 Kelvin. An increasing temperature of 500,970 Kelvin is incredibly hot, more than 90 times the temperature of the surface of the sun. The entire atmosphere would transform into superheated plasma, with the oceans evaporating and the Earth's crust instantly vaporizing. This event would be the end of civilization and would render the Earth completely uninhabitable. The meteor blowing up Earth, as in overwhelming its binding energy, does not occur, as Earth's binding energy is far greater than the energy of the meteor.
Meanwhile, on Earth.
Bro, where's Google Maps taking me? This route makes no sense and this doesn't seem like a good area. I hope nobody robs me and takes all my stuff.